let's do chapter 13 that is about analysis of variance. Chapter 13, analysis of variance, ANOVA, analysis of variance. Okay, if you browse this chapter, it looks pretty scary because it has many formulas, many tables, very heavy stuff on it. But let's try to figure out what is this about. Okay, let me start trying to explain you what ANOVA is used for. Okay, when we have two populations and we have a sample from each population and we have the hypothesis that the mu1 is equal to mu2 against that is not equal, okay? We have two populations in this case. Okay, when we have more than two, okay, when we have 3, 4, 5, or whatever number of populations we have, we are going to have the null hypothesis that the mu1 is equal to mu2 is equal to mu3 is equal to whatever number of populations we have against the alternative hypothesis that not all mu's are equal. Okay? So this is basically why we use ANOVA for. When we have two populations, we usually do the t-tests. When we have more than two, we use ANOVA. We can use ANOVA when we have two populations. But we usually do the t-test. Now, that is basically what ANOVA is used for. It's just to compare the mean of more than two populations. Okay, and in order to do that, we use the variance. That is why this process or this procedure is called analysis of variance. We have some assumptions in ANOVA. Two main assumptions. The number one assumption is that all population has to be normal, normally distributed. And the second assumption is that all the variance among the populations are equal. Okay, so what happened if, because the hypotheses are based on these assumptions, what happened if this doesn't fit? Well, the procedure ANOVA is very sensitive to these assumptions violations and might give you wrong results. But basically, these are the assumptions for using ANOVA, and if and this is very sensitive for this. If this doesn't happen, so be very careful on that. If you use ANOVA, you are going to be sure that the populations are normally distributed and the variance in these populations are equal. Okay, basically. So we want to know, for example, if one particular treatment or what they call factor really affect what is called my independent variable and the dependent variable. Okay, this independent variable is also called a factor that affects my dependent variable. This dependent variable is also called the response variable. And this independent variable is the one that we think that causes the variation on your dependent variable. For example, and this is the first example in your book, that we have three methods that's on page 510, A, B, and C. And we want to know if those methods are different from each other. And why we want to know that? Because we want to make some decisions about which of the methods to use. Okay. Now, since this is ANOVA, and I'm going to use some formulas that are in the book, okay? Because we need to know where the numbers come from. Okay, the assumption is that the total variation, or what is called in here the mean, and because we're going to see, at the end we're going to see the table, the sum of the squares, the variation, the total variation comes from the variation from the treatment or the factor that really affects my dependent variable, plus another variance from an error. Okay, and basically that's the main thing about ANOVA, that the total variation comes from the variation because of the treatment plus other variation causes by error. Now, and that is what is based on. So we are going to have the variances, two types of variances. The within variance and the between variance. The within variance measure the variance inside each one of the population's samples, and the between variance measure the variance among the whole population based on what? The mean of the total elements in your sample from all the populations. Okay, but basically, I have to give you this, I'm sorry. We have to have my X bar, that is the mean of all the sample points from all the population, and that is equal to the double summation of X of ij from all the j's and all the i's divided by the total number of elements in your total population. So your SSTR, the sum of a square due to the treatment, okay, is equal to the summation of nj times xj bar minus x bar squared. And that is basically the sum of a square based on this is the between variance, okay? And the mean squared, because of the treatment, is equal to sum of the square of the treatment divided by k minus 1, where k is the number of treatments that we have, or the number of population that we are dealing with, okay? And this is the between variance. Now, the within variance is really measured by the sum of a square due to the error, and that is equal to the summation of nj minus 1 times sj squared, and the mean squared because of the error is equal to sum of a square due to the error divided by the total number of elements minus the total number of populations or factors in your treatment. Okay, what's N? N is the sample sizes. NT is the total number of elements in your samples. X of ij is each one of the elements. X bar is the total mean. And we know then, having the mean square of the treatment and the mean square of the error, we know that F is equal to the mean square of the treatment divided by the mean square of the error. With how many degrees of freedom in the numerator is k minus 1 in the numerator, and in the denominator is n total minus k in the denominator. Okay? And this is going to be my test value, and I'm going to have my f distribution, and then I'm going to have a critical value over here, and this is going to be alpha, and I'm going to compare this test value, the mean square of the treatment divided by mean square of the error, and I'm going to compare with the critical value, and if it's in the rejection zone, I reject what? The null hypothesis that says that all the means are equal. So I'm going to reject, I'm going to say not all the means are equal. That's it. Which one is different? We don't know. We know that these are not equal. That's it. We don't know which one is which. Okay. Now, when we reject my null hypothesis, the book tells you to do what is called the Fisher LSD test to see where exactly are the differences. Okay? I don't do that. I mean, I really do not do that because there is a phenomenon that is called the inflated alpha, and in your book, that phenomenon is called the experiment-wise type 1 error. When you do multiple tests for one particular situation where you want to see if the means of the populations are equal or not, we would have what is called the inflated alphas. And then if you start with alpha equal to 0.5, then the first test is okay, but the second test is going to increase that alpha, and at the end you could have a rejection, or you find difference when there is no differences. So personally, I don't use that procedure to test where are the differences. What I do is I use SPSS software, and I use the post hoc analysis, usually the Chaffee or the Bonferroni test, and test where exactly is the difference. So I don't use it, nobody uses it, but you have to know how these things happen, and you need to know what is this inflated alpha problem means. But basically, I mean, I'm not going to go through the process. It's pretty simple. Is you use the t-test with nt minus k degrees of freedom, and it's exactly do the same thing. You do the t-test, or the test is xi minus xj divided by MSE, mean square of the error, times 1 divided by ni minus 1 divided by nj, and this is the test value. Sorry, it's plus. And this is the test value, and then you compare this test value with my the test statistic, and then if it's in the rejection zone, you reject, and then you say that I and j, the populations I and j are different depending on your alpha levels. But however, remember that these tests, when you do several tests of this type, you get this problem that is called the inflated alphas. So I just assigned one problem of those in the homework because I need you to know how to do it. Okay, but it's not that important. Also, there are many calculations in here, and you have to calculate the X bar for each one of the treatments. You have to have the number of elements in each treatment, and then you have to calculate the variance within and then the variance between, and do all those things. However, Excel do that for you. You just enter the data in Excel, and Excel is going to give you the data. So just enter the data in the computer, and the computer is going to give you the whole thing. Now, there are some things very important. When you use a statistical software, what you need to use, instead of the critical value approach, that is easy when you do it manually, you use the p-value approach, because the software gives you the p-value. So if the p-value is less than alpha, then what? You reject the null hypothesis. Otherwise, you don't reject the null hypothesis. So this is the rule of thumb when you use the p-value approach. What else? Another thing is that many softwares also present the information differently, but you need to know how to make the interpretation of that information. In Excel, it's called one variable. In SPSS, it's called one way ANOVA. There are many ways that you may have this information, but the important thing is that you know how these things work and how you have to make the interpretation of this data from the computer. Okay, what else? Okay, so sometimes you have what they call treatments or factors that you may say that affect whatever, the production process or your sales or whatever you are measuring. So you have 3 treatments, and at the end you need to have your X bar, your SS, and your Ns, and so on, okay? And then do all the formulas, but you don't have to do that. Excel does that for you. But the important thing is that the variance, the total variance, is because of the variance on the treatments plus the variance of the error. Sometimes when you say, and this is the blocking, this is the next part, that is the factorial experiment. Oh, no. This is the randomized block design. Sometimes you have your data, but you have some type of blocking that might affect your overall variance. Then you block it, and if the block is significant different, then you are good. However, sometimes, and again, the total variance is equal to the variance due to the treatment plus the variance to the error. Sometimes this error has the variance to the block plus the error. So you want to wipe out the block when you do this randomized block design. Okay? And the third part is when you have 2 variables. This is variable A or B or whatever, and this is another variable. When there's something else that you want to measure 2 variables at the same time, and this is called ANOVA with replication or something like that. So be very careful on how you use your Excel. And in SPSS, this is called the 2-way ANOVA, because there are 2 variables, 2 independent variables involved in the process. And you want to measure the effect of one variable, the effect of the other variable, plus the effect of the interaction between the 2 variables, and that is given by ANOVA. So you don't have to do that many calculations at all. So if you browse the book, it's very scary, but don't be, just enter the information on your computer, know which process to run, why you want to run it that way, and make the interpretation of the results. In the test, for example, I'm going to give you the ANOVA table, and then you have to enter the information that is in. by now, let's go to the computer and I teach you how to do these things.